physical science time. Let's call this thermodynamics. Please write down thermodynamics. Don't spell it with an X, but if you're looking for a rapper name, thermodynamics with an X at the end is not a bad one. Or I guess more like hip hop, or like dance hip hop, because that's not a very good rap name actually.
Thermodynamics.
No, just
Thermodynamics.
why not your name?
DJ.
DJ, yeah.
Yeah, like a hip hop
DJ.
mix.
Why not just dynamics?
You know what? Let's in the video there. That's everything you had to hear. No, let's actually let's break this word. Let's break it down, as thermodynamics would say. I'm on a roll. What's thermo mean?
Heat.
Yeah, it relates to heat. What's dynamic mean? This one's a little bit trickier, but if something is dynamic, what does it mean?
Flexible.
Okay, yeah, that's a good flexible. He said. What else?
The study of,
No, that's ology.
oh, right.
I like flexible's good. If something is dynamic, it means it's as opposed to static. Static and dynamic are opposites. So like static electricity is electricity that stays on a surface. So if static means stay, what might dynamic mean?
No.
It's kind of like movement / change. It means that things are changing relative to one another. So if we're talking about thermodynamics, what is that probably? The change in heat in a certain system. We talk about this idea of systems a lot, and this is one of the CCCs, the cross-cutting concepts in science, if you remember from the beginning of the year. You remember the CCCs, which are up there on that? One of them is systems and system models. You see that one, the fourth one from the left, the kind of teal one. It's also the fourth one from the right, because there are 7. But what's a system? In fact, just before we talk about exactly what a system is, what's the picture for system and system models on that little poster?
A tea kettle.
A tea kettle. What kind of system are they probably talking about? Yeah, thermodynamic system, because this is a very common kind of system that we don't. What are some other kind of system, as the other examples? The solar system. The solar system is a kind of system. What's other kind of? We use the word system in these other things. You have systems in your body.
Yeah.
You got a
Digestive
reproductive system. Okay, good. So systems are, well, how would we define system? Our 3 examples are digestive system, reproductive system, bone system, or I think you would call it skeletal system, even skeletal muscular system. But if those are examples, and the solar system is an example, and this thermodynamic system is an example, how might we define system?
System is a group of things.
Yeah, group of things.
Working
Tiana says
together.
things, group of, instead of saying things, let's say, do they have to just be objects?
No.
Do they have to be physical things?
No.
No, let's say group of,
Ideas.
let's say phenomena. What's that? We've talked about this before at the beginning of the year. What's a phenomenon?
A phenomenon is
A thing that happens. It's an event or an object or an idea. A phenomenon is a very, very all-encompassing word. A group of phenomena. I don't love when we say working together, because that implies that they have some kind of agency, like they can think for themselves. So we'll just say a group of phenomena interacting. They are interacting, which means that they are acting together, in between each other. They're doing things with one another. Well, a lot of times we would say, if I was teaching this to second graders, I would say they're working together. I would say that your cardiovascular system, I wouldn't say that word if I was talking to second graders, but your heart and blood vessels work together to give blood to all the parts of your body. It's not really working together because they're not really thinking about it. You don't have to think about your heartbeat. Anyway, systems are a group of phenomena interacting. So if we're talking about a thermodynamic system, what kind of phenomena are probably interacting? What makes heat? What is heat? Heat can be generated by friction. What makes something on a physical subatomic level? What makes heat
particles rubbing together.
not necessarily rubbing, but particles moving. Particles moving. How did your lab show you that?
Oh, like
You don't know. You
the
your
food
science.
coloring moving out.
Okay, and when you just so that we're clear, in case Cyrus or someone else was gone for the lab, what happened in the lab was you had 3 different vessels of
Yeah, I
water.
got that, yeah.
Of different temperatures. And we didn't measure the temperatures, but the temperatures were roughly what?
room temperature.
Yeah, room temperature, so medium,
Ice
hot,
water.
and ice water, which was low. So the temperatures were low, medium, and high, and then we put 1 drop of food color in each, and what was the result?
The hotter
one
was,
spreads
the
lower.
easier it was.
Yes, the hotter the water was,
Dissipated.
it more easily the food coloring dissipated. So particles moving, and then the greater their motion, like when the food coloring spread out faster, that also meant the greater the what?
Greater the heat.
Yeah, greater the heat. And that's all it is. I mean, this is what's called the kinetic molecular theory, or this is the main tenet of the kinetic molecular theory that we will talk about in chapter 15. For this right now, what we need to know is that greater motion of particles means greater heat. And when I talk about particles, what particles am I talking about? Sand?
No.
No.
Heat part.
Yeah, but no, there's no such thing as heat particles. The heat
Like-
objects have is because of what particle is moving. You know it. What particles is everything made out of? Atoms. Atoms.
Oh, yeah.
Atoms. So let's talk about these, some other ideas about heat first. The abbreviation for heat energy is capital Q. We're measuring the actual heat of an object, and I'm not talking about the temperature. We'll talk about what the difference between temperature and heat and thermal energy is. But if I'm talking about the actual heat that an object has, what things does that probably depend on?
Okay.
Okay, the movement of particles, which we determine as temperature. So that's one of them, temperature. What other things does the heat depend on? What would have more heat if I have a human being that weighs 90 pounds with a certain temperature, we'll say 98.6 degrees Fahrenheit, I think it's about 27 degrees Celsius, I don't really remember, 37 degrees Celsius, I'm almost certain it's 37. Anyway, a 90 degree human being weighing 37, or having a temperature of 37 degrees Celsius, or a 390 pound human being weighing 30, or having a temperature of 37 degrees Celsius. Which one has more heat altogether?
The guy with the weight.
Yeah, the big one. So what's the difference there?
Mass.
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 It depends on mass. It depends on the change in temperature. Here's that boy again. You remember him? What's heat?
Delta.
Delta, and that means what?
Change.
Change in. So M, delta T, and it also depends on this other quantity, C. And we're going to talk about what each of those means. A lot of times, this is the way your book has it, but a lot of times people, it helps freshmen especially to write it like this because it looks like something you can easily remember.
MCAT.
Cat. This morning, this is a side note. This is a side note that really has nothing to do with this. This is all around us, so that's my excuse. But this morning, I was leaving to come here, sadly, as I always do, and my wife was holding my infant son as I was leaving, and he kept saying, cat, and just pointing, and we looked around and there was no cat. But there was a bunny. And so he was trying to call the bunny cat because he doesn't know how to say bunny. And so we were trying to get him to say bunny, and he just waited a while and he went like this. Okay, maybe that's the bunny. Anyway, speaking of cat, that was where my side note came in. So Q is, as we said already, heat. M, lowercase m, is mass measured in
Newtons.
no.
I mean, Newtons. Kg.
Kilograms, yes. C is what we call specific heat, and we'll talk about what that means in a little bit more depth here. And the unit for specific heat is joules, kilograms per degree Celsius. We're aware of all these units, right? What does joules measure?
Energy.
Energy. And actually, I should have written Q is heat energy. It kind of was implied, but joules, kilogram per degree Celsius, and then delta T is what?
Change in temperature.
Change in temperature. I was going to trap you by having you just say temperature, but actually you're right, change in temperature. And what would we measure change in temperature in? Degrees Celsius, usually. This works out just fine, as long as if both specific heat and change in temperature use degree Fahrenheit or Kelvin, that still works out just fine, but just these two units have to drop out. And then we can see if our C, if our specific heat is measured in joules kilogram per degree Celsius, and we multiply it by kilogram, and we multiply it by, am I wrong? I am. It should actually be joule per kilogram degree Celsius, please forgive me. Joule So hopefully you didn't write this in pen. Joule per kilogram degrees Celsius. Sorry about that. Joule per. If you did write it in pen, what's the correct way to correct yourself in pen?
Cross it out. And then
Yeah,
you
put
write
one
it.
line through it and put the right thing above it or next to it or something. You know, I didn't do that because I want it to look nice and I want it to look like I'm not stupid. Even though I am. Thanks, guys. So if C is in joules per kilogram degree Celsius, and we multiply it by kilogram and we multiply it by degree Celsius, what do we measure Q in?
Q is measured.
Well, look at it. C is joules per kilogram degree Celsius, M is kilogram, and T is degree Celsius. So what's Q going to be? Joules. Joules. Does that make sense for heat energy to be measured in joules? Yeah, it does. Or at least to me it does, because we've talked about that before.
Yay.
Because I want you to, you will have practice problems with this as we do with any equation. You will have practice problems with this, but because I want to get through more stuff in the video, we'll do the practice problems outside of the video. Okay, we'll do them in class, probably tomorrow. Do you have questions about, does this seem like something you could solve?
Yeah.
For any of these? Most of the time you'll probably be solving for Q, but could you solve it for C, for instance?
Yeah.
Yeah, it wouldn't be that hard, we just manipulate. Remember to write the equation, then manipulate, then substitute, then solve. Make sure you have units all along the way. The next thing we're going to talk about, is, are you ready for me to erase this?
No, Mr. Kai, is on C specific key is joules over.
Joules over kilogram times degree Celsius. Other questions? Okay, I'm just going to erase this up here. I'll leave that down there for you, Hayden. You're just going to kind of look around me. So we're still talking about thermodynamics. The book does it in different orderings, but let's talk about the three, or there are actually four laws of thermodynamics first. I want to make sure that your book talks about all these so I'm not. No, it doesn't. I don't know why it does this. I'm going to have to look up at some point the what we call the zeroth and third law of thermodynamics. But let's start with one. So the first law of thermodynamics. First law of thermodynamics increase in thermal energy of a system equals the work done on the system plus the heat transferred to the system. Thermal energy, the total thermal energy of a system, we've talked about system, is equal to the work done on the system plus the heat transferred to the system.
Good morning, staff. Just want to let you know there is a coffee order going out. They will deliver today. If you would like to order, please have your order into the computer by 9 o'clock so that we can get that delivered. Thank you.
Okay. Well, this is part of my YouTube video. Now, coffee is not a sponsor. Other beverages are available. Yes?
What is the word right after thermal energy of a
System.
Of a system is what?
Equal to the work done on the system plus the heat transfer to the system. The main thing I want you to know about this is that we talked about work in the last chapter, right? Remember, we're talking here about physical work. That is work that pertains to physics, not homework or baling hay or whatever. We're talking about actual work. What was that? You remember the equation for work? I hope you do. What is the equation for work?
W equals FD.
W equals FD. And what was work measured in once we solved it? Joules. Because remember, work is a transfer of physical energy. Plus the heat. And what kind of thing is heat? What kind of thing is heat? We understood. It's energy. It's energy measured in joules. So what the first law of thermodynamics is really telling us is that the total energy of the system is the physical energy, the work, plus the thermal energy, the heat. Okay? It's just all the energy. Effectively, this is a restating of what? If we're saying that the energy of a system is equal to the energy in plus the heat that's already there, but effectively we're just restating what? The law, I'll give you a hint, the law of conservation.
Oh, conservation of energy.
Yeah. Of energy, yes, right.
What is the word under thermal?
Is equal to,
Equal.
yeah, law of conservation of energy. The second law of thermodynamics is super easy, or at least it makes a lot of sense, I should say. You can get in depth about it, and you can always get into depth in anything and make it difficult or make it complicated. But on the surface level, and for you little boys and girls to understand, the second law of thermodynamics is really quite simple. Second law of thermodynamics, and this is the one that I find that we talk about the most, maybe because it's simple. Heat energy flows from areas of high temperature to areas, guess,
Cold.
of low temperature. Yeah, of low temperature. And you've recognized this your entire life. The classic question, or at least it was classic when I was in elementary, is someone would say, why is it that when you have iced tea, we say that warms up? You don't want to drink it when it gets warmed up. Or if you have hot tea, we say it cools down. You don't want to drink it when it gets too cold. What's actually happening in both of those cases? The second law of thermodynamics. In the case of the cold tea, the iced tea, heat energy is coming in where it's hot out in the room, or comparatively warm out in the room. Heat energy is coming in to the cup, and it's warming up the cup. In the case of the hot tea, where it's hot in the cup, that thermal energy is leaving and going out into the room, and eventually everything kind of dissipates to be the same temperature. It all kind of averages out.
So how do we keep the same body temperature that is a lot higher than the room temperature?
Let me ask you a question about your question. If you die, do you still do that? No, so it's not a physical thing that's keeping you warmer than the room around you. It's a biological thing. And what that is there's a gajillion, that's an official term, a gajillion chemical reactions always happening inside your body. And we know from what we talked about last year that chemical reactions can generate heat. And most of the chemical reactions that happen in your body generate heat. And most of them do that deliberately. You know, like a snake or something that we say is cold-blooded. That's not an official science term. But something that cannot regulate its own thermal energy has a different type and kind of chemical reactions that occur inside of it than human beings do that can. So it's because of biological processes, which actually take a lot of energy. Where does that energy come from? Just
our food.
Yeah, your food. The food you eat and the way your body works causes chemical reactions that change chemical potential energy to thermal energy, and that generates heat. Yes, Peyton. Yes. Okay, I'm going to have to look these next two up, so I'm going to pause the video real quick. Okay, we're back. There are two more. We're going to put the one up here, because it was actually let's do the third one first. The third law of thermodynamics says that as a system approaches absolute zero, have you ever heard of absolute zero before? We're going to talk about that in a second. But as a system approaches absolute zero, the disorder approaches a specific minimum amount. Does anyone happen to know what we call the disorder of a system? You've probably heard this word before, but I would be kind of surprised if you actually could answer my question. Does anyone know what we call the measure of disorder of a system? No, that's all right. We call this, in science, we call this entropy. Entropy. We can kind of loosely think of this, once again, if I was saying this to second graders, we would loosely think of entropy as the opposite of energy. That's not exactly true, but they work in different ways. Energy we can think of in some context as the amount of organization a system has, the way the particles are organized. And we can think of entropy as the amount of disorganization, the amount of chaos in the system. A real basic example would be your room has more macro scale energy when it's organized and more entropy when it's disorganized. If you've got a big old messy room that has more entropy, you can think about it this way. It would take energy, and it does take energy for you to clean your room, right? You pick up, a sweatshirt, and you put it away. Oh, the dog pooped on the floor, put that in the trash, right? All of that takes energy to undo, right? Because it has entropy. It has a disorganization to it. But the closer we get to absolute zero, this entropy, the disorder, the chaos of the atoms, approaches some set amount, and it's different for different things. But what's absolute zero?
Negative 500 degrees?
It's about negative 450 degrees Fahrenheit, I think, don't at me. But I know that it's negative 273.15 degrees Celsius. And let's define it. It's the temperature at which what happens? Temperature at which, remember, temperature is the amount of particles moving. But what is it?
What's the word after
Well,
that one?
What?
Particles stay still?
Not quite, but that's what a lot of people think. But it's actually at which particle motion
Almost.
is minimum. So it never quite stops, but it's at the very, very closest to stop that it can possibly be.
And what is
So this makes sense. If we, now that we know that about absolute zero, give me a second, Colin. Now that we know that about absolute zero, that's when particle motion is at a minimum. Obviously, that would mean that the disorganization of the particles is also at a minimum. Colin.
I was just wondering what the definition was this for, too, because I can read the word.
Yeah, I can't either. Particle motion is at a minimum. The only reason I can read it is because I already know what it is because I wrote it. I know it's messy, but we're getting along. And then the last one that was kind of talked about or extrapolated, none of these were discovered, I would say, but we call it the zeroth law of thermodynamics. And because it's the most basic, they could have called it the fourth because it was discovered last, but they called it the zeroth because it's the most basic. And that is just that if two systems are in equilibrium, I'm just going to rephrase this one, it's a little bit simpler. If system A is in equilibrium with system B, and B is in equilibrium with system C, then A is also in equilibrium with C.
What transitive property?
Yeah, basically it is just a mathematical transit property. And you can see how it's more basic than all the other ones. And when I have this equal sign here, I don't mean necessarily mathematically equal, but I mean in this way. I mean in thermodynamic equilibrium with. So if system A is in thermodynamic equilibrium with B, and B is in thermodynamic equilibrium with C, then A is in thermodynamic equilibrium with C. The reason that's more basic is because it is a mathematical property, but it wouldn't have to be that way. Not everything in science is as it is in math. These things don't always go together in this way, but in thermodynamics it does, and so we call that the zeroth law of thermodynamics. That's the first postulate of thermodynamics. Do you have questions about that? How many thermodynamic laws are there?
There's like 3, but then
There's 3 in the zero, so there are 4 altogether. 3 in the zero. Loosely be responsible for knowing that, but these are more for your own personal use. Like you need to be able to use them to solve problems. So like there will be questions on your test that are like, as the temperature of this thing goes down, how does its disorganization change? That goes down too because of the third law. That kind of stuff. Okay, you have questions about any of these? There'll be conceptual questions. You don't have to have these memorized, but you need to be able to use them conceptually to solve problems. Okay? Questions? Okay, we're going to move on to the last thing we're going to talk about. And these are all definitional, so it shouldn't take very long. And they're also vocab, and they're also stuff we did last year.
Great.
The 3 methods of thermal energy transfer. By the way, let's real quick talk about the differences between thermal energy, heat, and temperature.
Well, what was the formula that we used?
The way back at the beginning?
Yeah.
Q equals MC delta T.
But
Thermal energy, temperature, and heat. Thermal energy is the energy something has because of its what? Energy something has due to its what?
energy something has because of its motion.
Yeah, the motion of specifically due to its motion of particles. If it's a big something, the actual energy it has because of its motion is called kinetic energy, but the kinetic energy of its particles is called thermal energy. So the temperature we could say is a measure of average thermal energy. So you're aware that the faster a particle is moving, the more temperature that lends the thing that it has that it's part of, right?
Yeah.
So does that mean my body is warmer than the microphone over there, just because of what we already talked about? Does that mean every single particle in my body is moving faster than every single particle in the microphone? No. But on average, the particles in my body, some of them might be slower than some of the particles in the microphone. Just like when you guys all take a test and I average out your scores, if your average was a 74%, that doesn't mean every single person got a 74%. It means that all together, and then divided by how many there are, you got 74%. That's what temperature is. It's the average motion of the particles. And then heat is what we call the transfer. What's the word transfer mean? Yeah, the movement of thermal energy. We call that heat. So when I'm feeling heat come off of a car hood, for instance, that's the transfer of that thermal energy from the car hood, which has a high temperature, to my hands, which have a relatively low temperature. There are three ways heat transfers. What are they? Does anyone know? We talked about it last year.
Three ways heat transfers.
Touch.
Yeah, okay, so we call that when things are touching and the heat transfer, we call that what?
Friction.
No, we call it conduction. Conduction is when they're touching or contacting.
So like through
It-
power lines? Well,
Yeah, that would be electrical conduction. We're talking about thermal conduction. Like if I touched the hot plate from the lab yesterday, the transfer of thermal energy there is because my particles are touching the hot plate particles, and the hot plate particles, which are moving really fast, make my particles move fast, and that is conduction because they're touching. What's another way? If I hold my hand above it, will I still be able to feel the heat?
Yeah.
Yeah, not as bad, and that's called radiation. Radiation, the transfer of thermal energy through space, and I don't just mean empty space, although this one can move through empty space, but just through the universe without having to touch, without touching. And then the last one is called convection, which is, once again, let's think about the hot plate. Hot. Yeah, that's better. Hot. It has to have a fluid in it, so we'll say water. Where is it going to get the hottest, this fluid? If this is the hot plate, the bottom, what's going to happen to it as it gets warm? Warm fluids do what?
boil.
Yeah, so they go where? Warm fluids
They
rise. And then when it's at the top, what's it going to do?
Dissipate.
It's going to, no, it's going to,
evaporate.
okay, maybe. We'll say it's not boiling, it's just hot. Hot on the bottom, and then it rises up, because it,
Bubbles.
So then
so then up here it's what? If it's hot down here, up here it's relatively cool. So then when it gets to the top, it does what? Cools down and begins to sink. And then this causes a little circle. So the convection is the transfer of heat as a circle through a fluid. Like boiling is convection. The mantle convects, which causes plate tectonics to move. Questions about the differences between thermal energy, temperature, and heat. You might use those interchangeably in real life, but you know the differences scientifically. Yes? Questions? Questions about conduction, radiation, and convection.
Sorry.
If you do have them, we're running out of time, so if you do have them, you can ask me later, or you can do your assignment.